Okay, everybody, welcome back to another edition of our project to do an XLR to USB audio card slash converter slash sampler, digitizer, whatever you'd like to call it. Today we're going to talk a little bit about a more boring component, which is the resistors and capacitors. These are generally things that a lot of people just design or download off of an internet or use one of the built-in Eagle packages, but there's a little bit to be learned about building these things, and in particular we're going to show you the process of how to make multiple packages on the same part. In other words, I'm going to have different sizes of resistors but not create brand new parts with them. So there's some fun you can have with that. Just like everything else, we begin with the data sheet. So the resistor data sheet will have the will have all the information from the manufacturer. And one of the things that's interesting about these things, and capacitors, chip capacitors, ceramic chip capacitors have this as well, is they have a standardized part numbering system, and the part size is equivalent to the 2-digit code representing its actual dimensions, right? So for example, we have some magic numbers like 0402, 0603, 0805, 1206. If you do the math, if you look at the conversion, or if you look at a data sheet that has things in both inches and in millimeters, you'll see that these 2-digit codes, or in this case a 3 and a 2-digit code, represent sizes in actual mils. So example, 0402 inch is 40 mils by 20 mils. So that's the sizing of it. And this one here, 01005, is 10 mils by 5 mils, right? So they added an extra digit to do it. So you can think of it as thousandths of an inch, and then they just drop the last thing. The catch is, somewhere along the line, people decided to take this inch-based system, which had been around for a while, and create an equivalent metric size system. And that in itself is not too terribly bad. It's just we ended up with some codes that are duplicates. 0603 has both a millimeter size and an inch size, and they're obviously very different sizes, right? They're off by a factor of about 4 or so, because 39 mils to, or millimeters, 0.39 millimeters to the tenth of an inch, right? So that's unfortunate. So when you're picking components and you pick out a size, make sure you recall whether these are inch or whether they're millimeters. Now Panasonic has done us a favor, which is that they've given us not just the mechanical dimension, but actually a land pattern, a recommended land pattern for the components themselves. And that's pretty nice, because you don't have to worry about how much heel and how much toe you have to give. And the smaller the part, the more critical that becomes. As the mass of the part goes down, surface tension on one side or another as the solder melts can actually pull the thing up on its side, and it's a process we call tombstoning. If you remember old cartoons where the guy dies and a tombstone kind of swings up out of the ground, that's exactly what happens here. This side may heat up slightly faster, and surface tension, capillary action begin to grab this side. Because the mass of the part is so low, it's actually enough to stand it up on its edge before this side has a chance to do its magic as well. So beware of really low mass parts, really lightweight parts. I'm not going to do all of these parts. I'm going to focus on just 4 of the most common sizes that I tend to work with, and they are 0402 inch sizes, 0603, 0805, and 1206. You notice 1206 and 1210 have the same width, right? 120 mils by 60 mils and 120 mils by 10 mils. You could use this package footprint for this one. They're fairly compatible. The catch is surface tension is also a blocker against that swimming effect. So as you've got extra solder on the side here and here, and as they do start to heat up, it may begin to kind of swim in the puddle of solder before it cools down, and it results in it cooling down and settling at an angle. So I will just use 1206 size for 1206 parts and not try to play that game unless I'm in a pinch. Then all bets are off. All right. So let's get to it. We begin with that piece of information in the schematic footprint editor or the package editor from the Eagle library. And what we're going to do is, unfortunately, Eagle's CAD capabilities are a little limited in terms of what we would like and what we would actually prefer to have. So here they've done us a favor in that they've skipped out 0201s and stuff, and 01005s and 0201s. Those are really good for really small devices like cell phones, but I don't think we'll use it. My favorite's 0603 because that's the size that they start to print the resistor values in ink on the front. If you remember the old wire style ones that had like color-coded bands, and there were all sorts of mnemonics of how to remember all those different color codes, that's great, but for these ones you'll generally end up with a 2 or 3 digit code, and it's just numbers. So 1003 means 100 and then 10 to the 3, so this would be a 100K resistor, right? And so that's what you see from below 603. There's just not enough space, and so you can forget which kinds of values you have, and they become a little difficult to work with at home if you take things off a reel and spill them on the table and forget which one they are. So we'll start with 0402s though, right? Now, because I said Eagle's CAD is a little limited, we're going to have to do some tricks because they drew dimensions that are different than what we want in Eagle. It would be nice if they put X by Y for the pad and then the center to pad spacing. But they haven't done that, so we have to do a little bit. We can either do a bunch of math or we can play a trick. So I like tricks, so this is what I'm going to do. First of all, I'm going to set up my layout dimension, right, or my documentation direction, which is new part. We'll call it R for resistor 0402. 0402 inch size resistor. So now we're done with description, and I don't really need you anymore. All right. So we start out with our documentation layer, just like always. And we set our width to 0, and I'm going to stick in inches for just a minute. Then I'll switch to millimeters, and this is kind of the nice thing about that, right? So I'm in wire mode, and I say half of my 0402, which is negative 0.02, and negative 0.01. And then again, positive corner. Back to that, terminated with a semicolon to end the wire command. So now I have the overall chip outline, and that's good. And the next thing I'm going to do is create another wire that I'm going to delete later on, and it'll be called, it doesn't have a name, it's still on T-Docu layer, I can put it in any layer, but it's going to match the A, B, and C dimensions that I want. So we'll start with A, right? And I want something that is A by C to measure out the center channel. So A by C is 0.52. Half of that is 0.26, right? It is negative. And I want my C dimension, which is going to be, we're going to take the largest one because I don't like to have chip pads hanging off the ends without copper underneath. So we'll take the 0.6 dimension, which is half of that is negative 0.03. Oops, I'm sorry. I had forgotten to do something. Now we're in measurements of millimeters. Okay, so now I'm going to do 0.1 millimeters with a spacing of around 2, let's say. Whatever. I'm going to be doing mostly typing in dimensions in this mode. So let's try that again. Negative 0.26 by negative 0.3. And again, positive corner because everything's nice and symmetric. Semicolon. Alright. Next I'm going to do the same thing. And I'm going to do the B dimension. And the B dimension in this case is 1.6, so half of that is 0.8. And I'll stick with the C dimension. That's fine. Positive, positive, negative, negative. I could have done a bunch of math, but I don't necessarily trust my own ability to do some math. Now, let's see, did Eagle do what I'd like it to do? Not quite. Okay, that's all right. So we'll do a little bit of math to figure out the SMD sizes, or we could do it empirically, right? Either way. And I've been playing with this before, so I got it kind of right. So I know it's 0.6 because this area right here is going to be what I have to fill in, right? And so my grid is not quite fine enough, so I'm going to set it up to 0.05, spacing of 4, and that's a little closer. See, now I can get kind of close. And remember, this is about surface tension and stuff, and so it's not rocket science. But anyway, the width that I went with after doing a little bit of math, or you could have done it empirically, was 0.55 by 0.6 millimeters, right? So cool. Now I'm going to give this guy a name before I go too further. You remember from before that it starts out with numbering them 1, and then the next one will be the next digit. So I'm going to call the first one A, just out of funness. And I'm going to fit it as best I can. This could be more precise. You know, I could look at it and do it that way and stuff, but I'm not going to. So this one's A, and this is kind of the best fit here. And then B for the next one. And I could have done my little mirror symmetry trick too if I wanted to, but I don't have to. So whatever. We're trying to get through this one. I'm doing a lot of talking, but we're trying to do it actually kind of fast. Okay, so now that I have my dimensions that match up fairly close with that to within a tolerance of something or another, then I don't need those extra dimensions, and I really don't want them to be part of my layout drawing and stuff. You also notice their recommended dimensions were just a little wider than the 0402/1005, right? So 05, so half a millimeter was the recommended thing, or was the package outline, and they said, you know, it's 0.6 at the max, right? So that's why there's a little overhang. So I was talking about them swimming, but you can see that this one's gonna be pretty good. We got a web that will form on the left and right if it's to nominal spec size, and everybody's happy. So now I can go ahead and delete things. Delete all those extra things that I don't need anymore. Because remember, my T-docu layer is generally about the actual size of the chip. Okay. So there we go. A couple of last pieces of housekeeping text on the T-docu layer for name. And you can see it's super huge, so let's bring it down a little bit, down to here. Sadly, the person who's going to be doing the layout on this is going to be, you know, maybe somewhat, they may have to do some zooming. And let's also make sure that we get onto the correct layer, because I don't want this to be on the copper layer. Right, so there's that on T-docu, and then I can use middle mouse if I want to, or whatever, to change to my T-placement layer, which you recall will be the, actually I'm going to go to, just because I got that open, the font is all ready and everything like that. Vector font, ratio of 12%, and a size, let's get it back to a normal size. Now, it looks huge by comparison, and that's because this is a small chip. So there's on T names, and now I can do wire T, oops, oh, I can't do it that way. Wire onto T placement, so I can draw a part outline. Now you notice this is the reason that I did part out, or the silk screen layer a little later. Let's get it to the proper width. Is I really don't want to cover any of this stuff up, so I needed to know how big the copper was going to be before I laid down this ink and stuff. So I can already tell that's not quite lined up. All right, there we go. Good looking layout and everything like that. Save our library and off we go. Okay. So the next portions of this is basically me following the same pattern down there. So we'll probably just fast forward through that. So not much for commentary there, but it'll be the same thing with just different dimensions. Okay. Alright, so we've completed creating all those packages, and they meet the manufacturer spec and everything like that. Let's make our symbol. We're only going to need one symbol for this, and so we'll just call it resistor. And resistors are kind of funky because I've not found a good way to draw them yet, but we'll try. I'm going to set it up with a pin with 0 length, so it'll be a point size pin. Point size. The direction is going to be passive, and the name will be A, but I don't really care. I don't want to see anything, so we'll turn both off. And I'm gonna set one side to the origin, and I'm gonna set the other side, I don't know, this far away. Now resistors get tight, so I want to be able to pack them kind of densely, so I'm going to break some of my normal rules on stuff. But first, let's draw the symbol. Alright, so let's make sure my spacing is, yep, that's good enough for what I want to do. We'll make the wigglies using the wiggly bend, I don't know, whatever you want to call it. And actually, I'm going to set up I'm using the Alt capability to go to a finer grid. You notice it's only about half as high as I normally do them. Okay, so that way I can stack 2 of them on top of each other and not have them look too janky, which is something that you end up doing a lot. A lot of series termination resistors, you stack them out a lot, and I'll talk about those kind of later. Anyway, let's add some attributes. So text, make sure it's the proper size, and font, because it does remember the last font you used in whatever the last Eagle tool was going to be, which in this case was the package editor, the footprint layer. Footprint editor. So I'm going to add more attributes than you might think. Obviously the name is going to be important, and I'm going to do some kind of clever justifying things so that things look sort of the way I want them to. Put the name here. I'm also going to use value, which goes on the values layer. And then I'm going to add a couple of extra ones. I don't normally do manufacturer part numbers, although I have thought about building up a database so that all the digit key parts for all the standard values are just kind of there, but I haven't gotten around to doing that yet. But what I really want to know, though, is an attribute that a custom attribute that I'll call tolerance. I'm going to put those underneath, and I'm going to put them in a layer. Let's create a new layer just for that. So creating a layer is not difficult. I just use the new command, and I will call it tolerances. That way I can turn this off if I don't need it. I called it tol before. I'm going to call it tolerance. I'll do the real deal, and I will put it on tolerances. And the last one that I'm going to have is power. So the power handling of a resistor is often important, and so I will create a new layer and call it power. Why not? I could have called it power values or something like that, but you know, whatever. And maybe I'll use this and maybe I won't on a specific design. Sometimes it depends on when you build the part whether or not you want to add that in. If it's there, it will end up on the bill of materials, which is often useful for someone who's doing part ordering. And so, so there we go. Lastly, I will probably do one other one that I'm probably just going to do on top of power, and it'll be called size. So how do we want to do this? Let's make a new layer and we'll call it package. I don't know, something like that. I don't want to be universal about that because I don't always put packages down, but in this case we do. I would like to give the user an option to have that. I think I'm gonna put it actually right on top of power or near enough to it, because I don't generally put both those at the same time. So if they want to see power, or if they want to see package, that's up to them. But they could use a smash command or something like that to separate those out if we want to. But now it's all there. Lastly, I do this for resistors and capacitors because they get so dense, is we're going to change the size of the font. So from our normal 0.7, we just use the wrench button, change size, and I'm going to make it 0.5. It helps you pack these things a little bit tighter. So that's what we'll do. And you almost always end up using a smash command to sort of make this work, but we'll see. I've never quite been happy with the way I do it, and that's no fault of Eagle. That's just simply I haven't found a style that I like for this particular issue. So whatever. Okay, there's my package, or there's my schematic symbol. Everybody's happy. Oh, one last thing that we didn't do before, and we're going to change what's called the swap level. And 0 means you can't swap something. 1 means I can. And I might decide at some point in life that I want to flip left and right. You know, and it doesn't matter for a resistor. It does for certain capacitors and other things like that. So there's a command that shows up in the schematic editor over here that just quickly will say, just flip these two around. And there's another one that's just like that does the same thing in the layout editor. So you can decide to flip pins on things, whether you're doing layout or whether you're doing schematic entry or whatever. Okay, so there we go. Now for the fun part. And the fun part is building the parts, actually. So this is where we build our device, and I'm just going to call it resistor. I haven't added any special names to it because all resistors are going to fall under this particular generic part. How do I decide which ones to use? Well, basically, I group them if they all can share the same symbol. And packages are just a different thing. So they're all going to use the resistor symbol, obviously. And they're all going to have the prefix of R. We can take up a little more space here, I suppose, now that we don't need that thing hanging around. I'm going to hold off on doing the description later for, you know, if you remember before I said sometimes these attributes get blown away. Right? So I don't want to do that yet. I want to do a new package, and I will call, you have to give these things a variant. We never had to do that before, where the first variant was okay. R0603. This will get appended onto the names of certain things in bills of material and stuff, which is why I don't use part names or the Eagle names. I don't make them the same as the manufacturer name. I use separate attributes for that. So we'll use -0603. I think that's right. R0603. Oops. Apparently I already did that. Let's do this again. Edit. Rename. And this is an 0402. Now we do a new one using 0603 package. Okay. And rinse and repeat for 0805. And 1206. Okay. And all of these are going to have the value turned on, meaning the value button in schematic is a direct entry. I'm not going to do a whole lot of attributes on stuff for this, like I did manufacturer part number, vendor part number. I have not built up this big database of all that stuff that I would like to do. That's a good job for a ULP program, which I may talk about later on. But I do want to set up the size, and I want to set up that to be for 0402 is going to be 0402, and I'm also going to set up power, which usually is 1/8 watt. This is why I usually use size and I don't actually do power. And I'm going to set a tolerance, 1%. I always use 1% resistors. I know you can get them in 5%, but the cost is like so super the same. Now look at this. I set up all those things, but I only set up for 0402, and that's gone for 0603. There are variants where they call it technologies, that you can have attributes be shared, and there's kind of a neat thing to do that. But those have to have the same package, right? As far as I know, I haven't figured out how to do it any other way. So we'll just set that up again. Tolerance, 1%. Power, 1/8 watt. That's kind of a placeholder. That's probably for that size. It probably would be at 1/10 watt. Size is the important one. 0603. I do want that to generally be displayed. What else did I put on there? Yep, that was the only ones. And these are editable, right? Because I'm setting them up to be variables, so someone could change them. You can do clever stuff with you know, things later on and stuff like that. That you set things up to be constant so that the person can't edit them, and that could be sometimes a reasonable way to do it. Alright. Not much to it. Save and done. Building capacitors is largely the same, and I'm only going to do one capacitor package here, and that's just to basically demonstrate something that's really neat. Remember I said before, multi-layer chip capacitors have the same sizes, right? So let's pick a size, R0402. And I'd like to be able to copy and paste stuff. Oh, by the way, let's hope I didn't blow stuff away when I connect these. Yeah, I forgot to check. I forgot to connect them. It's because of this thing, which is a feature, I'll say, of this version of Eagle that I don't necessarily like, which is it comes scrolled all the way super wide. It would have warned me if I had attempted to use the thing and say, hey, this has unconnected pins and stuff like that. So anyway, now everybody's happy. Now I can save. Alright, so back to building capacitors. And I want to build a capacitor package. I'm going to make it a unique package because that's why I gave these things R suffixes. But I'm going to start with 0603 just because I don't know why. I really don't like using 0402s, but they have some really neat things, especially if you're doing controlled impedance traces. But anyway, I'm going to build a copy of this thing. So what I'm going to do is I could go up and build it this way by saying, you know, library, package, and then pick one of them, or I can do, you know, I can right click and say edit package. Anyway, this is how copy and paste works in Eagle, which is a little bit strange. Okay, it's not Control C, Control V, and the words mean something different. So the first thing that we're going to do is we're going to group everything. So that's good. Now that it's grouped, that's actually already copied. Okay, and then cut is not the same as it is in Windows because it's not going to delete anything. It's just simply going to say what is the origin point for a future paste operation, right? So cut is kind of finishing the copy in that it sets up the origin point, which I'm going to set the origin point to be the same. Boom. That's it. That's all I have to do to be in the copy proper operation is to group and then cut. Okay. Now I can create a new device or a new a new package, and I'll say C non-polarize 0603. Would you like to create a CNP? Sure. Okay. Now I can use the paste button, which is this guy right here, and it's as if I have everything done. This is the best way to move back and forth between things, and sometimes to get yourself out of mistakes that you've made that you can't seem to get out of, like deleting a package that is in use or something like that, or adding pins to a package that's in use. That's a common problem that I have. Okay. So anyway, I've just created an 0603 size package based off of an 0603 size unit. Let's double check a couple of things and make sure that it is in fact an 0603. Quality assurance, right? 0603. That's all. If I was really judicious, I would go to the data sheet and make sure that these pins match up. But this is more to demonstrate the thing than actually to build new chips and stuff like that. So I think we've served our purpose by just showing one demonstration of that. Okay. So last thing for that is to go ahead and build its symbol. So I'm going to call this cap non-polar. And the reason is, you know, for those of you who've done electronics before, you know that there are a difference between polarized and non-polarized capacitors. And they have different symbols. So let's go ahead and draw a pin. It's going to be passive. It will be swap level 1, so I've saved some steps here. Same things as before that I don't really care about showing any extraneous information. And we'll call this one A. And we'll call this guy B. And building capacitors is kind of an art too, because I always try to align the pins. In fact, I always do align the actual pinpoints on the big grid. But then what do you do in the middle? And I like to stack capacitors on. So I'm going to make this one a little tighter than normal. It's a little shorter. Okay. And again, using my Alt command, boom. Make it look nice and symmetric. Boom. This is going to be a fun one because we get to use the arc. And the arc has got a little personality of its own. So it didn't quite give me what I wanted. As you can see, what it's trying to do is it's trying to find a point on the radius already. So that's why I say arc has a little bit of a personality. Okay, so let's try this again. I'm going to try to put it here. And that didn't quite do what I wanted either. You have to imagine the full circle. And then make sure that that full circle is a part of what you want to build. So. Oh, I miss AutoCAD and its massive array of different ways of drawing arcs. That program is real nice. Alright, that's kind of the shape that I want. I like that curvy thing on capacitors. I don't know why, I've always liked it. So let's move it in for the kill. Start lining up these ends. And voila. There's a I just accidentally drew a polarized cap. You know, that'd be a better polarized cap symbol because it's got the curve. But let's not let it go to waste, right? So let's take and do our copy and paste trick. Kind of got ahead of myself there. Cut. Oops. I hit paste instead. Cut from there. Now it's in the buffer, and I can use it again as long as I don't do anything in the cut. Again, that stuff is still in there. Gets a little strange when you try to cut and paste from schematic to layout and stuff, but for the most part it's okay. So let's delete that curve that I spent so much time on and just make it a kind of a boring capacitor. Maybe give him a little room. Good enough. All right. So now let's add our attributes. I kind of wish I had pasted that thing. I probably should have just finished up the polarized cap and renamed it, but whatever. So let's add ourselves some attributes. Text. Name is of course always there. And I'm still in my smaller font, and that's okay because this is going to be one of those other ones that I do a lot of kind of high density work with. So I'm okay with this capacitor being a little smaller. Value. And then another important one is dielectric. So capacitors have a lot of interesting values on them, right, that you want to keep track of. Oops. I'll change the layer in a second. And finally, voltage. Not finally, I still got a couple more left to go. And I want to put that on a layer called voltages. Actually, I'm going to put yeah. And size. Fortunately, I already have a size layer that I created before, right? Didn't I? I did package, right? Now, there's a lot of stuff on here, and I kind of need it all. So maybe making this such a small capacitor was not such a good idea. But if anything, I will probably in a real circuit lose the size, because all the rest of them actually become kind of important, or maybe I'll lose the dielectric and just have a note that says everybody's a standard of dielectric of blah blah blah. So you know, there's that. Okay, so let's fix that dielectric problem. I want to make another one called dielectric. There's another way to do this too, that you can make things invisible as you do the schematic capture, which is another option, right? Apparently I had two of them there. Two of them on top of each other. Alright. So there's that. Okay. So what I'm going to do is I'm going to cheat a little bit and create another polarized cap. Oops. Cap dash pol. Okay. Paste my magical symbol, and then I'm going to jump back a little bit and copy all that extra detail that I created. So back to symbol, cap and P, and just do the same thing again. You notice when you do the group command, all you need to do is get the origins. I don't need the whole thing, and that's important to know because that will help you explain why it is you captured a particular line that you didn't think you should, and things like that. So the little origins for insertions, that's how it gets its thing. And I'm gonna put it there. I go back to my other symbol, paste it. Look at how much time I saved. Okay. And last but not least, I'm going to add just a little, I'm going to change this a little bit, this polarized symbol, because change swap level to 0, because I can't swap a positive and a negative. And I'm also going to change the names from A and B to plus and minus. And lastly, I'm going to add just a little bit of text that says plus on it. And I'll put it on the symbol layer. and that way it's kind of stuck with everybody. Actually, you know what? I'm not going to do that. I'll tell you why. Because when you do a smash command, it will separate that text out too, and I never want this plus to go too far away, so I'm just going to draw it as a little plus sign. And that's looking a little small, so maybe there we go. So now I always have a nice little plus right next to it, and it can't be smashed away or removed or anything like that. And I don't know, maybe I've changed that. Nah, I'm not going to mess with that. Okay, we had enough fun with this. So that's that one. And now we have, let's go ahead and finish up our capacitor thing. Add my non-polarized capacitor symbol. Prefix C. Package. We only have one that's there, but I'm going to do it as C NP 0603. Connect. Attributes. Dielectric is going to be X5R. And I'll talk a little bit about those dielectrics at a later time. I'll set up a voltage to be, I don't know, 16 volts. We'll change that on the fly anytime we use it. Size will be 0603, and that was it. And voltage is turned off. Okay. So I'll go ahead and copy and paste and do the rest of that for the rest of the resistors, or copy those resistor packages into the capacitor packages, and call it done. So, fast forward, imagine. Okay, we just created two sets of polarized, non-polarized caps, and a whole suite of resistors using the different kinds of commands. So we should be getting through a lot of the boring stuff, and I hadn't seen a whole lot of people doing this kind of thing. To build the polarized caps, which is probably a separate video because we're running out of time, will be very much the same. It's just I will be using the polarized symbol, and we'll do the exact same process. We'll look up parts and we'll build them. So this is about an hour's worth of work to get us through all that stuff. You can see that for the most part we accomplished quite a bit. In the next time we will build up those capacitors, the remaining capacitors, and then get into in probably the one after that we'll start looking at a couple connectors. And connectors have their own interesting things. So we'll see you then.